Hi, my name is Adan Benito, and I'm a PhD student at the Center for Digital Music in Queen Mary University of London. Today, I will be presenting the work that my co-author Andrew McPherson and I have carried out to evaluate a novel approach for the acquisition of musical gestures on the electric guitar using tunneling magnetoresistance sensing. I will start by introducing the concepts of gestural ambiguity and direct acquisition on the electric guitar, and then proceed to describe the sensing setup, followed by its characterization based on the obtained data. Finally, I will showcase some applications of this technology for transcription and augmentation. Since its invention at the beginning of the 20th century, the identity of the electric guitar has been shaped via its adoption by different musical traditions. As a result, distinct idiomatic playing styles have emerged, and with them a recognizable gestural palette that musicians use as a resource to convey articulation and meaning. The expressive gestures associated with producing sound can usually be divided into modification, fretting, sliding, etc., and excitation, that is, energy transfer gestures. Due to the variety of different techniques and the division between left and right hand gestures on the guitar, capturing this poses an interesting challenge. One reason for this lies in the fact that some gestures, despite being linked to different physical interactions and perhaps presenting different significance to the performer, might have similar, even identical, sonic results and be hard to tell apart from this perspective. The projection metaphor proposed by Jack et al. In 2017 to describe performer-instrument interaction presents a good framework to look at this issue. According to this model, actions that are projected through the instrument pass through a point of reduced dimensionality before being expanded to sonic and kinematic behaviors. The bottleneck that determines which gestures are rendered into musical meaningful outcomes and affects how the player develops different patterns of interaction. From this perspective, gestural ambiguity can be seen as a set of gestures that, when projected through this bottleneck, are made indistinguishable from each other, producing a very similar sound. One fundamental case of this behavior for the guitar is picking direction. Downward and upward picking movements are virtually indistinguishable from a sonic perspective, and yet quite important for several techniques guitarists employ. Moreover, gestures like trills, rapid alternations between two consecutive notes, can be achieved on the electric guitar via slurs, hammer-on, hammer-off alternations, and portamento, sliding between adjacent frets. Another example of ambiguity comes with the performance of vibrato, which could be axial, bending the string perpendicular to its axis, or longitudinal, when the string is pressed on its axis against the fretboard on an oscillatory manner. Similar to picking direction, bend direction can also result ambiguous, as the pitch of the played note will always be raised regardless of whether the bend happens upwards or downwards. Even more dramatic is the case of pre-bends, where the string is bent before plucking to perform a downward pitch shift, as they do not have an immediate sonic effect and can only be perceived after a whole event has occurred. Researchers have tackled this problem in the past by using sensors for capturing parameters of expressive gestures during performance. This has the effect of expanding the instrument's bottleneck, and when using the design of instrument augmentations, has proven to be able to allow performers to repurpose their existing expertise and therefore retain access to virtuosity for different families of instruments. More specifically on the guitar, the focus has been on left-hand gestures, using for example capacitive sensing to extract fretting articulations, or on the right hand, using pressure sensing for picking and palm muting gestures, or capacitive, magnetic, and even inertial sensing for picking and strumming. There have been several commercial attempts to extract real-time string bend information. However, only a few focus on direct sensing of the string's movement. Guitar-like MIDI controllers from the 80s like the Syntax and the Yamaha G10 already employed embedded coils on the fretboard and optical shutters on the bridge respectively to account for string movement. More recently, other technologies have appeared for this purpose, such as piezo-resistive film tailpieces, strain gauges under the bridge, and even inductive sensing as in the Keith Macmillan Stringboard 2. However, of these many technologies, only the Syntax offers information of bend direction for when it operates under monophonic mode. Our proposed approach is based on tunneling magnetoresistance sensing, a phenomenon based on the idea that electrons have a magnetic moment whose direction varies with magnetization. TMR devices are composed of magnetic tunnel junctions, a structure where two ferromagnetic layers are separated by a thin insulation barrier. One magnetic layer is free and the other one fixed so that the tunneling current of electrons changes with the magnetic field orientation. When the direction of magnetization of both layers is parallel, the current flow on the barrier layer is large, and therefore the resistance of the MTJ element small. When it is antiparallel, the current flow is small and the resistance large. The particular sensor that we chose for our prototype is the MVE AAT00110E, a low-power angle sensor that has two perpendicularly pinned half-bridged MTJ elements and offers two sinusoidal outputs for sine and cosine components. In our evaluation arrangement, the sensor lies underneath the guitar string with its sensing plane, xy, parallel to the string and perpendicular to its main axis of vibration z. X is orthogonal to the string's longitudinal axis, while y is parallel to it. The string is magnetized by two axially polarized neodymium magnets that are equidistant from the sensor. When the string is stationary in the x-axis, the magnetic flux saturates the TMR sensor, offering a constant DC offset reading. When the string is plucked or bent, a displacement is provoked on the non-fixed end of the string and the magnetic flux is shifted along the x-axis, with the sensor being able to capture its change of direction. The horizontal displacement will therefore be proportional to the ratio of the sine and cosine outputs of the sensor. To acquire these signals, we designed a breakout board where cosine and sine outputs are amplified independently using a low-power op-amp in non-inverting configuration as suggested in the manufacturer's datasheet. The amplified sine and cosine components are digitized with a 16-bit SAR ADC available on the Bella embedded platform. Audio from the instrument is also captured by Bella together with the analog signals in a sample line manner and without jitter for the posterior analysis. Using the DC offset of the stationary string as a boundary, we can differentiate between upward and downward string bends with a sensing range of about 1 volt peak to peak. However, while characterizing the sensor, we observed a great trade-off between sensing range and monotonicity. While the range is highly dependent of the sensor position relative to the string and the bridge, greater displacements cause the string to stop being magnetized, resulting in a non-monotonic response. The video shows this effect for a downward bend. Notice how, when the string goes off range, the reading returns to the DC offset value even though the string hasn't been raised. We also appreciated some hysteresis on the sensor readings. See how the displacement value for the upward bend on release ends up above the threshold for the DC offset caused by the stationary string. We believe that this is not due to the sensor itself, but to the magnetization of the string and the effect of the finger releasing it when it is displaced, rather than bringing it back to the rest position. This did not impede us performing a relatively simple pitch-based calibration of the sensor readings for different string bends. In order to do so, we captured a synchronous audio and sensor data stream. Pitch contour was then extracted from audio using the melody algorithm and split into different note segments via island building and RMS power thresholding. Note segments within 100 milliseconds were aggregated to create articulation groups. On the other hand, sensor data was used to compute the estimated displacement and thresholded to obtain upwards and downwards bend sections. Mappings between displacement and pitch shifting were then produced for upward and downward bends via quadratic regression. The resulting second-order polynomials can then be used to map displacement to frequency for each direction. We can see how the predicted contour after mapping approximates quite closely the pitch contour estimated with Melodia. However, since the amount of displacement necessary for an equal pitch shift varies depending on which fret is being used, a piecewise mapping will be necessary to characterize a string given the whole fretboard. This calibration allows us to obtain automatic enhanced transcription for audio excerpts that accounts for string bend direction in a relatively simple manner by looking at both the estimated pitch contour and sensor data. For this purpose, the pitch contour segments associated with articulation groups are split into individual nodes with the sensor data being segmented as well according to the node boundaries. For each node, a linear approximation via least squares regression is obtained for both sets of data. Slopes from each linear segment are thresholded to select bend nodes. Afterwards, the slope sign is used to derive the attack and release sections of the string bend based on the pitch contour slope. If both slopes have matching signs, it is an upward bend or release. On the contrary, if both slopes have opposite signs, it will be a downward bend or a downward release. Another use of the sensor data is the determination of plucked onsets and their plucking direction. We compare onsets obtained from the audio stream with peaks shorter than 100 milliseconds on the sensor data. If a peak matches the position of an onset, then we can annotate this as a plucked onset. The sign of the peak indicates the plucking direction, and the absolute height is related to the intensity of the excitation. This setup can also be used to create relatively non-intrusive instrument augmentations that expand its control possibilities. We run a real-time pitch tracking algorithm on Vela based on gene pitch detection and time domain pitch synchronous overlap and add for manipulating pitch. The estimated displacement from the sensor data is captured by Vela, low-pass filtered to eliminate bends due to peaking, and thresholded to obtain upward and downward bends. The obtained values are then mapped to pitch shift quantity using the process described earlier. A simple scaling factor can then be used to modify the target frequency of the SOLA algorithm to alter the bending rules. This video shows an example of how the bend rules can be easily inverted with downward bends producing downward pitch shifts contrary to the normal behavior of the guitar. In this presentation, we have showcased a novel methodology for the direct acquisition of musical gestures using TMR sensing. We have shown how a string displacement can be used to infer left and right hand gestures. We have portrayed how a pitch-based characterization of our sensor can be used for real-time estimation of musical parameters. This technology can be used for heuristic gesture disambiguation using multimodal sensor and audio data for those sets of gestures which produce a similar sonic output. In the presentation, we have also demonstrated a couple applications of this technology. The first one being the enhanced transcription of string bends and plucked onsets. And the second one, a novel way of doing augmentation on the guitar that is non-invasive and that preserves performance expertise. For the next steps, we would like to characterize these sensors for different frets and multiple strings, using an array of TMR sensors together with a hexaphonic pickup to extract more complex gestures. Thank you for your time. Do not hesitate to get in touch if you have any questions about our work.